Okay. So last time we were talking about linkages. I did one example problem, but I hadn't really given a detailed set of steps for doing linkages yet. So I'm going to start with that. Basically, like describing how to solve linkages in the simplest way is this. Solve the kinetics for each rigid body in the linkage, and then come up with joint constraint equations so that your number of equations match the number of variables you have. When you finish solving the kinetics for each individual rigid body, you're going to have more variables than equations. That just has to be the case because in these linkages, there are requirements that this body and this body, the two bodies that are connected, usually by a pin joint, agree about where that pin joint is. Okay? If you could solve the equation without that, without knowing that that joint, they have to meet at the joint, then it's not a linkage. It's just a collection of stuff floating around, you know. Okay, so here's a general method for linkages. So for each body in the linkage, find the equations of motion using Newton's second law and rotational Newton's second law. So this step one here is where you fit all those steps that I gave you just for a single rigid body. Okay. So notice first, if there's no fixed point, no, the opposite of that. If there is a fixed point, if there's a fixed point for the rigid body that you're doing, then your about point is going to be that fixed point. Then you're not going to use Newton's second law. Okay, that's the step 5 that I gave you in the steps for individual rigid bodies. And second, if you're doing 2D problems, which is going to be the vast majority of what we do, then how many equations do you get from Newton's second law and rotational Newton's second law? How many useful equations? You get Newton's second law gives 2 equations. Rotational Newton's second law gives 1 useful equation. The other ones are just 0 equals 0. So you get 3. If you're in 3D, how many equations do you get from Newton's second law? 3, yep. And rotational Newton's second law, how many equations do you get there? For general motion in 3 dimensions, the angular acceleration, the moment, those are just general vectors, right? Remember, and the direction of those vectors is like the instantaneous axis. Okay, so that gives 3 more equations. So you get a total of 6 equations. Second, look at the variables that you have in this new set of equations and reduce the number of variables. If that applies using Newton's third law. Okay, so you have this new rigid body, say body 2. One of your force vectors is the force on 2 by 1. You come up with your equations, and then you look back at your last rigid body and you say, oh, I had force 1, 2 in that one. So Newton's third law says I don't need to define these two new variables. I can just use negative F12. Okay, so we'll see how that works. Then make a new list of your variables. And list and number your new equations. And repeat these 3 steps for every rigid body until you're done with the whole linkage. Okay, step 4. Count the variables and equations. You can solve if those numbers match. You can't solve if they don't match. So from this, you can figure out how many constraint equations are needed. And then your constraint equations, step 5, the joint constraints. Say the acceleration at the joint according to one member has to equal the acceleration at the joint according to the other member. So that's a simple idea. What equations do you use to define that joint constraint? You'll use this one. The acceleration is equal to angular acceleration crossed with r plus omega cross quantity omega cross r. Excuse me. You'll use this one always. And then you'll also use the relative motion equation sometimes. And what are the cases where you're going to use this? Well, you're not going to need it if your about point is a fixed point. You are going to need it if your about point is the center of mass, because that center of mass, well, you are going to need it if your about point is anything other than a fixed point, okay? Because the thing that you're doing all your motions relative to can have acceleration, okay? So if A is not fixed, and this acceleration here in the rotation equation, in the acceleration equation, this acceleration is, well, what term in this equation is it going to represent? Yeah, exactly. Okay, so before we go on to some other examples, let me go back. I think In statics, I know when I did statics, we talked about all these, and I'm sure probably you did it in your statics too, but it'll be good to have these in your notes. So let's just go back over the different types of joints and what type of loads you need to put on your body according to each type of joint. Okay, so 2D joint types. And the type of loads they apply. So first, by far the most common when you're talking about linkages are pins, but you treat those the same as hinges, and you treat those the same, actually. This one isn't immediately obvious, but contact with friction. So a pin or a hinge usually is drawn something like that. This is contact where friction is assumed. The joint then applies to each adjacent body a full force vector. And so the number of variables that this joint introduces in 2D is 2. Second, a roller, a pin in a slot that can slide along a slot, or a frictionless contact. So these look like this. There's a roller. There's a pin in a slot. Here's a frictionless contact. Looks just the same as the friction contact, but it'll say that you're assuming that it's frictionless. And so even though these things look the same in drawings, descriptions of problems, you have to treat them different mathematically. In this case, you have a force vector, but we know the direction. With this category 1, we don't know the direction, so we have 2 variables. Here we have a force vector in the direction perpendicular to the contact, or perpendicular, let's say, to the surface. So how many variables does that introduce? You can represent that with just one variable. Okay, you know the unit vector, and then you're just multiplying the unit vector times a single scalar. So the number of variables in 2D is just 1. Third is a fixed or a weld joint. These are a little, you can treat these as a joint, or you can just treat both of the 2 things that are connected as a single body, But if you want to treat this as a joint, and it'll look just like this, or like this. This will apply a full force vector and a couple. So the number of variables in 2D is going to be 3. Number 4, a weightless cable. And actually, let's do these. I have these in my notes separated into 2, but let's do a weightless cable and a weightless member together. So in problems, these will appear like you'll have a member like that connected by a cable, you know, or you'll have 2 members connected by this little piece here that, you know, a lot of times the weight is negligible compared to the rest of the forces in the problem. In that case, we have a force vector along a line between the connections. And so the number of variables there is 1. There are a couple of cases where, so like for example, think of a contact with friction as opposed to a pin joint. Think of a contact without friction as opposed to like a pin in a slot. And also think of these two in relation. They're treated the same mathematically, but one of these types restricts more motion than the other type, right? Like this member is free to hop up into the air, right? This one isn't. Okay, if this was connected by a pin to the floor, it wouldn't be free to hop up into the air. So what does that mean that they're treated mathematically? And it's the same with those other ones, like this cable and this. So say that this cable was a weightless member, okay? They would both be equally good at keeping this member from pulling out to the right away from the wall. But the cable wouldn't have any ability to keep the member from moving closer to the wall, right? But the member does. So mathematically, I said they're treated the same. How does that difference show up? Well, so what you do actually is the variables, all the math is just the same, but then after you get your answers, you need to inspect it to make sure it makes sense, okay? So in this case, so we have 2 variables, right? In this case, if we end up with a force saying that it's pulling the member down, we know something isn't working. Our model, like usually all that means, okay, if you're doing a problem like out of a book or whatever, it means you did something wrong. If you're doing a real engineering problem, it means that you don't want to count on, you know, support with contact with friction here because it's not going to make the linkage do what you want it to do. Okay, so you need to, in those cases, just inspect those forces and make sure that they're what you expect them to be. And same thing with a cable. If this cable is applying a pushing force away from the center of the cable, then you know that can't be a cable there. And in whatever you're designing, you better put something else there. Okay. Okay, so let's do some, let's look at some examples of just what these loads look like in free body diagrams. So how would you represent these? So first, say that you have two members connected by pins. This is probably, I don't know, 90% of the joints that you're going to see in linkage problems are just two members connected by pins. So let's say this is member 1 and this is member 2. So in the free body diagrams for member 1, you'll have a full force vector. In the free body diagram for member 2, you'll have a full force vector on 2 by 1, and then you can reduce those variables as negative F12. Okay. So when you're solving a linkage, in this case, those are going to be variables you're going to have to solve for, and that's more constraint equations that you're going to have to come up with. Okay. For that second type, any questions? Maybe I don't want to race through this too fast, but I know you guys have seen this kind of stuff before. Okay, so for the second type, say you have a pin that slides along this slot. And let's say this is member 1 and this is member 2. Then in your free body diagram for body 1, you're going to have a force that's perpendicular to this slot, instantaneously perpendicular to that allowable motion. I don't know, call that R. And in your free body diagram for member 2, you're going to have an equal and opposite force R. So these are perpendicular to that slot. And what if that slot or the allowable path is curved? Then what do you do? Not that much math probably, because you'll probably have to know where in that slot you are, and it's just instantaneously perpendicular, you know. For that third type, so say you have a weld joint. Call this member 1 and this member 2. So the free body diagram for member 1, you have a full force vector, so that's F12, and you have a couple. I'll call that M12. And then the free body diagram for member 2, you have F21, M21, and F21 is equal to negative F12, so you can reduce the number of variables there. What about the couples? Well, I think it makes it pretty clear if you think about what a couple is. You know, like a couple is just a pair of forces. And you know that Newton's third law applies to both of those two forces. So Newton's third law also applies to couples. So M21 is equal to negative M12. And you can reduce the variables that way. And then the fourth type. So say this is member 1, this is member 2. The free body diagram for member 1 is F like that. Free body diagram for member 2 is equal and opposite, so F like that. So if this is a cable, you know your answer for F better be positive here, or else a cable isn't going to work. Okay, because you know the cable has to be pulling the two things together. You know, if this is a rigid member like this, that F can be negative. Okay, that's the difference between a cable and the member. Any questions about any of those? Okay, so this is the thing to remember. So like that's a lot of detailed information, but you don't need to remember that detailed information if you just sort of internalize this. The loads applied by a joint are determined by the motion that the joint doesn't allow. Okay, so that's how whatever kind of joint you have, you don't have to go back to a table or whatever. You can just think about what kind of motions the joint does or doesn't allow. So let's think about these. Like a pin joint. A pin joint doesn't restrict any rotation, right? But it does restrict translation in the X and Y direction. Okay, so there's going to be a force in the X and Y direction, and that's what we have, and there's not going to be a couple. Okay, those forces appear due to the motions that are not allowed by the joint. Okay, this one allows motion side to side, so there's not going to be any force component in the direction of the slot, but it doesn't allow motion up and down. So that's the direction of the force that's applied. And it doesn't restrict rotation. This member 1 could rotate around in circles, so there's no moment. Okay. So you can think about like all of these work like that. A fixed joint doesn't allow any translation or any rotation, so you have everything covered in the loads. Yep.
Just with the pin in the slot, why not let the force directly then pin it at the end of the slot and then you have another?
Yes.
So
yes.
That's just for a pin not in contact at the end.
Yes, that's right. Yep. Any other questions? Okay, I have an example problem that I'd like you to think about. Okay, so you have this linkage that's instantaneously an equilateral triangle. This is member 1, this is member 2. I guess I have these lettered, the joints are A, B, and C. The mass of each of the two members is 10 kilograms. And say that you have a 200 Newton force applied at the top and a 50 Newton force applied at the side. And the length of each member is 1 meter. So 60 degrees, 60 degrees. That's equilateral. And instantaneously, the angular velocity of body 1 and the angular velocity of body 2 are equal to 0. What's the acceleration vector of that pin at B? Or of the roller at B? Yep.
In the steps you go through languages,
Mm-hmm.
the first was just to solve all the individuals.
Right.
In statics, you would first kind of treat this as a whole, like solve the overall rotation.
Yeah. That is not going to help you here. Why is that? Let me think about that. That's not going to help you here. So, but let me think about that while you guys are working on it. So just start with the individual members. Also, by the way, right now I don't have a set of practice problems up on linkages, but I'm going to put a set up. So look for that. And also the new quiz is up now in the new lectures. So we're going to get back into those quizzes. And we're going to be doing more of that dancing on Tuesday. So if you might find some Ally McBeal on YouTube or something.
Some of that problem set,
Mhm.
I talked to you
Okay.
on Monday.
Yeah.
I was trying to figure it out that angle.
Yeah.
Maybe if I found the equation for the tangent line,
Uh-huh.
I understand what's if it crosses the x
Uh-huh.
axis, and then I think you take the dot product to find the
Yeah.
tangent. So I did like that, and it was a lot of work.
Yeah.
I mean, the way that he showed on the board was much is, and then I was playing with that. All the slope does is shows the direction. Right?
Yeah.
To get first derivative.
You use that to get a unit vector for the velocity vector. So yeah, come on in.
Yeah, that was much easier.
Yeah, it is much
After
easier.
I did
Yeah.
all the dot product and stuff, and figured out my vectors, it seems to be a lot of work. That was
Yeah.
a lot easier. So what I did was I found it to be 45 degrees. So I just rotated all the way to 360.
Mm-hmm.
That turned out to be 315, I believe.
Right.
So instead of doing like rotating 45 degrees, like you said, and then over the x-axis by 180. Just did 360.
Yeah.
2Ds.
Right. Okay.
Turned out right, like I checked my.
Okay. Good. Perfect. Okay. See you later.